We will be designing a look-ahead carry adders. This design is in response to this question. The question says, show that the additional logic circuit necessary to make the 4-bit look-ahead carry adder, the one in the figure here in front of us, into 5 bits. So, in other words, given this 4-bit look-ahead carry adder, extended to be that of 5-bit. So in other words, we have here these 4 adders. We have 4 of them. We need to add one more here. Okay. And in effect, we need to come up with the equation that describe the carry out adder. So in other words, here we try to find the equivalent of the C out 4. So somehow here we need to come up with a solution that give us the C out 5. So this is the whole point of this question. But before we proceed, we need to really appreciate the idea of the look-ahead carry adder, and the best way to do that is to contrast it with the simple yet inefficient ripple carry adder, the one that in front of us here. So we have here 4-bit. This is the ripple carry adder, and you can see how this one works. You have the least significant bit being added, and then if there is a carry, it will be some here, some result, and if there is a carry, will be propagated to the next, right, to the next one, and the same for the second, and so on. So in other words, the inefficiency of this design is that the adders to the left can't proceed. They have to wait. They have to wait until the one before finish. You can think of this as a conveyor belt where some workers putting part, assembling some parts, so they can't proceed unless the previous worker has completed their part. So let's look at some example here. So we're going to add 2 numbers. The first number, we're not going to name them A4, A3, A2, A1, and the second B4, B3, B2, B1. Let's take some concrete example. Let's say we have 1 0 1 0, and this is the equivalent of 10 in decimal. And let's take 0 1 1 0. This is the 6 in decimal. Let's add them and see how it will this design will carry out. So here this is the A1, this is the B1. So A1 and B1 here will be 0 0. So the addition will be carried out, and we're gonna get back the results 0. So this we're gonna have 0 here, and what is the carry? 0. Okay, in other words, there is no carry. All right, this is the carry. It will be available here for the next one. And then when we for this part, what we have here 1 1. All right, you can see them here. So when you add these, then the result will be 0. All right, and we have 1 carry. The carry will be here and will be available to the next one. Okay, so what we got now for the next one, we have 0 1. All right, again, when we add, we're gonna get 0, and we have 1. Here's 0, and we have 1 carry. We'll be able to the next one. So in the final one, we will have the carry is already 1, and for the A, we have this it is 1, and this one 0. Okay. So when we add, the result will be 0, and we have 1 carry. So 0 1. 0 1. So we end up with 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 0, 0, 0. So you see it here. And the 1, 0, 0, 0, this is really just 16. So you can see the result is really correct. 6 plus 10 is 16. So what the important thing is that we notice that is the any of the subsequent, any of the next adders like this one cannot start unless the first finish. The same goes for the third and for the fourth. And although this design is simple, it's not efficient, it's not fast. So this is for 4-bit. If you have 16 or 64-bit in maybe in real life situation, this will really slow down the calculation. And this is what prompts the desire to design a faster one. And here where the look ahead carry adder. So what we're trying to do, we're trying to avoid this waiting. We try to avoid these. We're going to eliminate these. And the idea here is based on the observation that the carry out is coming from the two parts. One part is called the carry generation or generator, CG1, which is based on the observation that when we have when both A and B when both A and B are ones, we can immediately know that there is a carry. I don't have to wait. I already know based on that. Okay, and some other part. We're gonna see where this one come from. But these are our data that will be used to derive the equation. So again, let's emphasize what we're trying to do. We're trying to eliminate these parts. Okay, we want to do these. We want to have a way so the addition can happen simultaneously. What that mean? This one and this one and this and this should be able to do the addition at the same time without any further delay. And let's look at the truth table. This is truth table for that's representing the input. So this is the input, this is the output, this is the carry in. All right, and we try to devise, all right, the value for this guy. All right, and very simple. You can use logism evolution. In a previous session, we talked about how to use logism evolution to design, but it's easy to design. What is important here on this part is we have all possible combination, and you see here 1. Why 1? Because we have a carry here, because 1 plus 1 will be, the result will be 0, and we have a carry. All right, same thing goes here, these. So whenever we see there are more than one, then there must be a carry. So the carry are in these cases 1, 2, 3, 4 cases. So next we will be using Carnomap to get the sum of the product that express this equation. Okay, and here is the Carnomap. And in the Carnomap, we see that we have 3 groups. You have, this is one. Let me highlight them different colors so we can see them. So we have here one group, right? And then we have here another group here. Right? And finally, we have the third one. We have three groups. So recall that in Carnomap, how it works, we group a power of 2, and we group the one that are neighbor cells, and then we try to figure out the final one. So we have the 3 groups. The first group here, this one, the one you see it in blue, it just has what? It has C. You can see the C is there. So for this one we have C. Okay, and then the B, the A will be cancelled, so we have CB. And for the next one, for the one in green, we have C, all right? And this time the B will be cancelled, we have CA, all right? And the final one, the one you see it here, so the C will be cancelled. What is really left is just A and B. So these are the three terms, 1, 2, 3 term. So this three term can be written in this way. Okay, so this is really the expression that represent what's happened with the carry. So this one will be important for us in driving the equation. This part is called the G, the carry generator, and this part is called the carry propagator. You will see G and P in the next slide when we talk about the equation. Okay, now that we already figure out how to calculate the C out, so we're gonna use that information to find the carry out for the other adder. So you're gonna find for this C out 2, 3, 4, and ultimately the C out 5, and this is really what the question is all about. But we have already done the hardest part. Okay, so the first one is already given to us by using the Carnot map. We found it here, and recall this part is called the CG, the carry generator, and this part here called the carry P, the carry propagator. So you see them here, okay, and the same goes for the rest. So what is the C out one then? It's just exactly this equation. We have it here. So this is done for us. Now we're gonna use that information to find the C out 2, this guy. And we're gonna be using the crucial information that C in 2 is the same as C out 1, the one we just calculated. And this one expressed in this equation. Okay? Okay, and then we know the C out for any of these is following this equation, with respect to the adder. So for the C out 2, then it is the generator plus the propagator times the carry in. Okay, and you can see this is true for all of them. You see it here, so we don't have to repeat. So exactly the same thing. All of these are species, all of them, of this equation, and we're done with this. So I don't have to repeat that. Okay, so the next crucial thing is we notice here, in order to solve this, I need to know this guy. And fortunately, we have the equation here that tell us I can replace C in 2 by C in out 1. And this is what we have done here. We just rid of that and we replace it with its equal according to this equation. And why we did this? Because we already calculated this from the previous step, which is this guy here. So what you see here is just, this is just C out 1. We substitute its value here. And then we have a just simple distribution. We multiply this value by the component on the inside here. It give me this. We do the same thing for the C out 3. Okay, again we substitute here, and we know already what is out C out 2, which is here, calculated from this step. Okay, we just substitute it here, and we do the same thing for the C out 3. Okay, so now we are pretty much done. But before we proceed, let's notice that every C out, every carry out consists of two terms. So this is the two term. Sorry, let me repeat. It consists of some pattern. Let's look at the pattern. For C out one, we have two terms, the first term and the second term. For the second carry, we have three terms. This is the first, the second, and the third. And for the third, we have 1, 2, 3, 4. And for the fourth, we have 1, 2, 3, 4, 5. So we expect then for the C out 5, for the S5 they are looking for, to find 6 term. And we're going to see on the next slide how we calculate that. So here in front of me is the repetition of C out 4 because we're going to need it. So how we find the C out 5? We repeat what we did because Cn 5 equal C out 4 like we did before, and then C out 4 equal the propagator, the generator plus the propagator time the Cn5, and again we replace, replace it here, replace Cn5 by C out 4, and C out 4 we already calculated here, so we're gonna replace these wholes, this by this whole term, and you will see it here. All right, and then the final thing is we distribute. We're going to distribute this, multiply with the whole thing, and ultimately this will give us this result. So in front of us here is the final term, and we can verify, and we'll see we have 1, 2, 3, 4, 5, 6 term. We follow the same pattern. So this is the answer to the question. So I'm gonna leave it as exercise that you use a combination of and an OR gate to for the design. It's very straightforward final step.